I think some logistic updates. So I have posted the homework 1. It's available on EE class. I think the setting has changed. It didn't send any email, but I would make an announcement for those that they missed to check the EE class platform. You have 2 weeks to complete your homework. I just give you an extra week because I understand that you want to study for the midterm, which is the next week. So just have enough time so that you can answer your questions. It is typical, you can write it down on a piece of paper and then take a picture, convert it to the PDF and upload it to the system, or you can, just type it in some word processor, whatever is your favorite. And just to make it easy, it is better if you can just convert it into the PDF so that your TA can easily open it and grade it. Yeah, these are the 2 updates. Any questions regarding midterm and homework?
How do we take the midterm?
Okay. Can you elaborate a bit more?
Yeah, I mean, we take the exam online or?
Oh, yeah, it's gonna be online. So you're gonna be at the comfort zone as you are right now, and the homework, the exam would begin exactly at the same time. And then you would have, it would give you extra 20 minutes or 30 minutes for you to, once you're done with your answer sheet, you can, if you write it down, take a picture, convert it to the PDF, or you get enough time so that you can prepare it and upload it to the system. The exam is going to be open book, which means that you have access to the material. So just study beforehand so that you can understand the material, and then you would be able to answer the questions. I think we would have a strict some rules, and when it comes to the next week, we will talk about it. The rules doesn't really affect the way that you want to answer or whatever. Just try to prepare as you are preparing for any other course. I think the only difference is that your exam is going to happen online.
Okay, thank you.
All right. So let's begin with what we've started last week. I think, well, I kind of wanted to a bit rush it to finish this chapter last week, but well, we couldn't. We have a lot of material left. So I feel like that I kind of rushed it a little bit too much for the last 2 pages. So that's why today we would recap the last 2 pages before we continue and make sure that you kind of completely understand the last 2 pages that we discussed. So remember that we were talking about the groups and subgroups, and then we run into a very interesting theorem that about generators, or you can use one element from a set so that you will be able to generate the other elements in a set. So let's start with our famous example of Z star 5. So remember that to make it clear, we have so far 2 groups. We have Z5, and then we have Z star 5, right? Remember that these are a little bit 2 different groups. So when we are talking about the Z5, we are typically talking about the group with the addition operation. So we have elements 0, 1, 2, 3, and 4. And then the operation is plus. And then when we are talking about the Z star 5, we are talking about a group with multiplication operation. So we said that in order for this to become a group, we have to have inverses, identity element, and all, and so on and so forth. So because of that reason, 0 cannot be a part of this group. And the reason for that is that 0 doesn't have an inverse. So we would have 1, 2, 3, and 4. And then remember what was the definition? What was the definition of this group? All the elements that are co-prime to this number over here, 5. So if you recap, so we have Z star n is a set of number such, greater than x, greater than less than n, such that GCD of x and n equals to 1, right? So all the numbers that are co-prime to this n. And why is it so? Because if that is the case and these are co-prime, we can assure that every element in this set has multiplicative inverse, and that was one of the most important things in order to have a group. Other than having closure, and we have identity element, we have to have multiplicative inverse and associative rules. So these are the two things that I hope that I just brought it up in case you forgot. So going back to our discussion, we were talking about the Z5. And then talking about the subgroups, we noticed that we can represent the subgroups with this notation. And typically, we take this element from this group, any of these elements, and we start to raise them from power 0 all the to power n. And then we do the computation, 0 to the 1 to the power 0 mod 5, 1 to the 1 mod 5, 1 to the 2 mod 5. And no matter how we continue, we'll see that we would only generate element 1. So this means that this is an element that is generating the subgroup 1. We take 2, for example. We take 2 to the 0 is 1 by definition, mod 5. 2 to the 1 is just 2 mod 5. 2 to the 3, 2 to the 2 is 4 mod 5. And then 2 to the 3 become 8 mod 5. That 8 mod 5 becomes 3. And then if you continue to 2 to the 4 becomes 16, mod 5 becomes 1, and we just stop, right? So the smallest integer that, after that, the whole thing would start to repeat itself. So there's no point to continue. And why is it so? We said that previously we had this theorem that if you take any element from this set, another rule, that if you raise it to the order of this group, mod 5, you always get 1. So the order of this group, Z5, is we have 4 elements. So any element I take from this set, I raise it to the power 4, I'll get to 1. So that's where I would stop. And as you can see, when we continue, some elements like 2 and 3 happen to generate the entire group, but with a different order. And we know that it doesn't matter. There's no order in a set. All it matters that they have the same elements. And one of these elements, which is 4, it happened to only generate these 2 elements. And it's interesting, when we raise 4 to the power 2, we get, we would just stop and we start to reproduce 1. And that is where we stop. So this is the order of this 4. Because this is the subgroup, is a generator, what we call it, of this subgroup that has 2 elements. So this subgroup has 2 elements. We get 4 to the power 2, we get 16, mod 5 becomes 1, right? So that is the highest degree that we get. So that was interesting until we get to this page that we said that there are some groups, and this is very important for cryptography, that there is an element that it would generate the entire subgroup. For example, if you're looking at this Z5, there is at least one element, 2 or 3, just one of them is enough, that this element, when you raise it to the different powers, it would regenerate the entire group. But this element is very important for us because, imagine that you want to use one element and then do cryptographic things. So we want to make sure that this element would generate the entire set. Otherwise, if it is a generator of a smaller subset, even though you choose a huge prime, you kind of produce a very small set of numbers, and breaking the system would be easy. We are interested to find an element that we call a generator that basically covers the entire set. And that means that when you generate a huge prime, you actually have a huge subgroup or a huge group to work with, and breaking that, we call those groups to be safe. We will get to there and have some examples very soon. And then we said that if there is a group that the order of the group is prime, we happen to be a prime, and then that group is for sure cyclic, and every element is a generator except the identity element. And then we said that there is a way that we can find the subgroup of another group that we can that was another part of the discussion. I think the most important one was this last interesting thing. So we said that suppose that we are given that the order of the group that we are going to work with is m, some integer m. And then, so there is an algorithm, there is a way to test if some, integer that you find, some element from this group, if you find, to test whether this is going to be the generator of this group or not, whether it would generate the entire set or it would just generate a subset of this group. And then in order to do that test, we need to make sure that we need to, first of all, decompose M into its prime decompositions. So maybe M is like 15, and then you can say that 3 and 5 are the prime decompositions of this integer. And since you have 3 and 5, according to the Lagrange theorem, remember that a subgroup, there could be potentially there is a subgroup for a group, as long as the size of that subgroup is a divisor of the size of this group, right? So if there is a subgroup for this group with size m, the size of the subgroup can be P1, P2, P3, or P4, P all the way to Pk. So that is given. Now we get to our algorithm to see how we can find the primitive roof. If you're given any, integer n, or we have now restrict ourselves to a prime p. So the way that is going to work is that you choose a random g, and suppose hopefully this is going to be your generator. And then what we would do is that we take that g, we raise it to the power p minus 1 divided by pi, and we make sure that this is not going to be 1 mod p. But why is it so? Let me go back to the previous example. We said that over Z5, we said that in Z5, 4 is a generator of 1 and 4, and only 2 and 3 can pass this test, right? So we know that, the only, the size of this group is 4, so it is 2 times 2. So we need to take any element, raise it to the power, have it like, we need to take any element and do this test. Our group size is 4. We divide it by the size of the subgroup, which is the divisor of 4, the prime decomposition of 4. And then 2 to the power 2 is 4 mod 5 and is not 1. So this 2 would pass the test. But if we were to choose 4, for example, we get 4 to the power 2 becomes 16 and becomes 1 mod p. And we know that this is not a generator of this group Z5. This is actually a generator of a subgroup of Z5, which is the subgroup of this group, right? And this test would correctly detect that. So what we have to do is that from now on, we know that whenever we want to choose a generator, this is going to be our algorithm. First, we need to have the prime decomposition of that group size. And then we would randomly choose a G. And then we would make sure that, when we do this calculation, the remainder mod P shouldn't be 1. And if that is the case, and it passed for all of those, then we can just return G as our generator. And if it fails, well, we get unlucky. We choose a generator that is not happen to be the generator of this group. So we go back and we test another integer. And the density of the generators in most of the groups are high enough that very soon we would find a G and as a generator, and we would basically halt. As a rule of thumb, most of the time, we choose 2 or 3. We start our test with G to be 2 or G to be 3, especially if the order of the group is, prime. Let's say the order of the group is, some prime number. So 2 is already guaranteed to be the GCD of 2 and that prime order to be 1. And that is a very good indicator that, there's a highly likely 2 is going to pass this test. And if not, maybe 3, and if not, maybe 5. But majority of the time, integer 2 happen to be a good choice. There's no concern of which of these elements you choose as a generator, as long as it is a generator of the entire group. That would pass the test, and we can make sure that this group is safe. So there are some other conditions that it would get back, that how do we choose this prime, or this integer n over here. There are some rules, or whenever you choose a prime p, there are some rules to make sure that you don't have multiple subgroups, or at least you have a subgroup that is very huge. So those are the things that we want to make sure that it happens to have a safe group. And then very soon we would start to discuss about that. So that being said, so we said that the Z star P is a cyclic group because we can always find a generator for this group. So Z star P, again, let me write it down, that Z star P, to have a generic example, is a group that has this element 1, 2, all the way to P minus 1, right? It has all these elements because this is not n, this is P. We always denote it as a prime. So all these integers less than P are co-prime to this P. So they would always pass that test. And that's why, this prime would be always a good choice. But the size of this group, something that we should always be careful. The size of Z star P is, what is that? That is P minus 1, right? We are not including the 0. And you need to be careful that P minus 1 is not a prime number. So it does not mean that every element in this group is going to be a generator, right? We said that if the group size is prime, then that group is for sure cyclic and every element is generator, but it is not the case for every ZP, not Z star P. So we need to make sure about that is the case. And then in case that you're wondering how many generator exist for this group, that number is going to be phi of P minus 1. So let me make it clear that you always have this notation that phi of P denotes the size of the group. We can also denote it by this. And for given P, that is P minus 1. Now to make sure that we don't get lost, so this is the size of the group. And then there is another number that denotes the number of generators of G, which is denoted by phi of P minus 1. So this has totally different computation. P, we know that P is a prime. So P minus 1 is an even number. And I can't just write down what is the answer. So when you have an even number, you have to decompose that even number to its prime decomposition. And then we already gave the formula in the beginning of this chapter, how you can compute given that prime decomposition or prime notation representation of this number, you can compute the phi function. But that is already going to be a huge. So there are a lot of elements on this group that are generators. And then, as I said, if you run our previous algorithm, soon we would be able to find one of them. Okay. There are two other important things that sometimes you would run into them. There are some cryptographic algorithms that are built upon some groups that we call them quadratic residuosity. We are not going to discuss them very often on this course, but just for your information, that these are also forming a sort of different group. So we are talking about given this Z star phi, there are some elements that when you raise them to the power 2, mod p, they have solutions. So let me show you what does that mean. Imagine that we are again in our Z5, Z star 5. So I get the elements and I raise them to the power 2. Of course, mod 5. For every element, I'll repeat the same thing, mod 5, right? And let's see what are their answers. 1 to the 1 mod 5 is just 1. 2 to the 2 mod 5, it is going to be 4. 3 to the 2 is 9. Mod 5 is going to be 4 again. And then 4 to the 2 is 16. Mod 5 is going to be 1, right? So according to this definition, the set of quadratic residusity of this, set 5 is going to be 1 and 4. And the set of quadratic non-residusity for 5 is going to be 2 and 3. So another way to look at this is that there are some integers, some element in this group that when you raise them to the power 2, mod 5, you get 1 or 4, right? But there are no elements in this group that when you raise them to the power 2, you get 2 or 3, right? So that is the definition of this quadratic non-residusity. This would form a group if it is quadratic residusity, and they would form a different type of group that we have different types of cryptographic algorithms that they would depend on this. Since this course is applied cryptography, we tend to just talk about those algorithms that are quite applicable, and you will see them throughout the internet. But for example, if you are interested, we have an encryption system called Robin's encryption system. And if you see the definition, they use this quadratic residusity and non-residusity to do the encryption. So the encryption algorithm is based on this quadratic residusity group. Just it's an information for you. If you see it in future, don't get panicked. That is where it comes from. And it's very interesting that when you choose this P to be odd, which is the case, like for example, for us over here, then the size of these two groups are exactly the same, and it's just like P minus 1 divided by 2. So we have 2 elements in quadratic residusity and other 2 that are not. So we just cut them in half. And then, so there is a note here. Sometimes we want to compute the kth roots of an element, and then sometimes in some condition, we know that finding the kth root in general it is very hard. It is a hard assumption, but sometimes it is very easy to compute, and we need to be careful when we are doing cryptography things with it. So what do we mean by that? Assume that we are given we are working on ZP star, and then we are giving an integer a, and I ask you find the kth root of this a. So find x such that when you get x to the power k, you get a mod p. So this is what we are looking for. So we are given the group Z star 5, Z star p, I'm sorry. And then you choose an element where A is in this set. So somebody's giving you A, giving you P. And the question is that find some X that when you raise X to the power K, then the remainder is A mod P, okay? And it happened that sometimes, normally there is no easy way to find such an X, K is also given. And let me put it this way, K. Sometimes it is easy to compute. Normally, it is very hard to compute this K. The best known algorithm that we can find this K is to iterate over all possible X's. And we know that when P is large, then, there would be many different X's. So it is computationally infeasible to find this X. But it turns out that sometimes it is not the case. If you don't choose K carefully, and if happen that K is co-prime to P minus 1, to the size of this group, right? So we know that the Z star P, the size of this group is P minus 1, right? And we have a rule that for if you take any A, you raise it to the order of this group, mod P, you get 1. It's always the case, right? According to the Euler's rule. If you take any element from Z star P, you raise it to the power of the order of this group, you always get 1. So, this is trying to rhyme something in your head. So if you choose K to be co-prime to P minus 1, not P. If you happen to choose that bad K, then this means that the GCD of K and P minus 1 is going to be 1. And that means that there is an inverse for this. You can use a extended Euclidean algorithm to compute the inverse of K. So that means that you can find a K that when you multiply to K prime, it is going to be R times some integer R, P minus 1 plus 1. We can find this equation using Euclidean algorithm. So given that, once you find this inverse of K using the Euclidean extended Euclidean algorithm, then all you have to do is that you get the A, you raise it to the power K prime. A is to the power K, K prime, and then let me write it this way, that is power K, mod P. Then this is equivalent to writing it down as A to the power R times P minus 1 plus 1, right? Which is going to be mod P. So this is going to be equal to A to the power 1 times A to the power R times P minus 1 mod P. According to the Euler's rule, I know that if I take this A and I raise it to the order of this group, I get 1. So that means that this part is going to be 1 because A times P minus 1 is going to be 1 multiplied to R. This is going to be 1, and 1 to the power R is going to be 1 anyways. And that means that the answer of this equation is going to be A, right? So therefore, if you happen to not choose a right integer, a right K, then solving this equation can be very easy. So we need to be careful about that when we are going to use, raising these numbers to the power K in the case of cryptography. So that is something to keep in eye. All right, so here is one of the most important parts that we want to talk about. And we talked that, we always have ZP, Z star P, and we never made it clear that, okay, there are many primes out there, but which prime is a good prime to work with? So here is a very important slide for us, and we are going to talk about the safe groups. So let me denote Rn is a set of prime numbers that they have n bits prime numbers. You can imagine that is a set. And every prime has this format. Q is a prime. 2 is like an integer, but it is interesting that 2 times prime plus 1 becomes another prime. So this guy is a prime. And this guy is also a prime, right? So the way that we normally generate this prime, if it is your question, we normally find a prime Q, and then we multiply it to 2 and plus 1, and then we test if the resulting P is a prime or not. The probability test algorithm is deterministic algorithm, and we can do it very quickly to test to make sure that P is prime. And if that is not the case, we would drop the Q and we would find the next Q. And we would just keep continuing doing that. So let's suppose that I have done that and I already have a set of, this sort of primes that we have like n bit primes, and I have a set that is denoting to that. So why is it so important that we have to have this? Before I go forward, I want to make something very clear. We said that the size, when we are generating this group, so we say that the subgroup of this group, if I'm talking about this Z star P, then the size of this Z star P is P minus 1, right? According to the definition here, this is going to be 2Q plus 1 minus 1, which is going to be 2Q. That is going to be the size of these safe groups. According to the Lagrange theorem, then this group can only have 4 subgroups. The subgroups is going to be the one itself, and then the subgroup, the next one is going to be Z star P itself. These are the obvious subgroups. We would have another 2 subgroups, maybe exist or maybe it does not, that we call it H, that the size of this H is going to be either 2, or we have another subgroup H prime that the size could be Q, according to the Lagrange theorem. Remember that the size of the subgroups of a group is the one that can, divide the order of the group. So the only integer that we have that they can divide the size of this group is 2 or Q. It could be. It is not guaranteed, but if there is such a subgroup, that is the case. But why did we choose this prime to be like this? According to this description, if this is my group P, it is very important that, when you choose a generator, you happen to have a generator that is generating the entire P, or if it is generator of a subgroup of this P, it should be huge. So according to this definition, I would have the subgroup of size 2 over here and a subgroup of order Q, which is huge. And given this, I specifically designed my group so that I can have maximum 2 groups. And let's say in worst case, we have both these subgroups. And if I happen to choose a correct generator, let's say this integer G over here is going to be my generator, then this generator is going to be able to generate the entire, elements in this subgroup. And that's why we call it to be a safe group, because, we can generate we have a group and we have a generator that the generator can generate a very huge group. Okay, we don't restrict ourselves to a very small subset. You still might wonder, why is it so? Soon we will get there and with some examples. Okay, now we understood that why do we design or choose our P to have, this specific size. So we have the assumption. We assume that there is no probabilistic polynomial time algorithm that can solve any significant portion of this, discrete logarithm problem where you choose this P to be like this, as this is a prime that is 2Q plus 1. And G is is a generator of this group GQ. It's not a generator of the entire set. G is a generator of this group Q, which we call it GQ. Okay. So formally speaking, let me finish this one, let me finish this one, then we go with some example. So formally speaking, for any probabilistic algorithm A that can, it's algorithm A that is our adversary algorithm that can claim that it can solve this issue, they can, break this assumption. For some k greater than 0, we would have some M0 at some, primes with M0 bits, maybe up to there, it's easy to pre-compute this entire groups. But there would be some M that, is going to be greater than this M0, maybe up to, remember this M is the, is going to be, or a set of primes, M bit primes. So let's say if I choose M to be 10 bits, then I can go and find all those prime numbers that are 10 bits and they have this format. And I can go and pre-compute all those, exponentiations, mod p, and I keep them in a table. But it says that, at some point it's going to be infeasible because of the computation and the storage restriction. That it says that if you happen to choose from, if you choose a, big prime numbers that they have M bits that are larger than that you cannot, afford to pre-compute, and then you choose the correct, generator from GQ. And if you take any element from Y from GQ, and you pass these things to the adversary and ask your adversary to compute the discrete, the inverse of the discrete logarithm problem, the chance of this adversary to win would be 1 minus m, 1 over m to the power k. It's going to be less than some negligible function. And as you can see, interestingly, the more you increase your size of m, the more larger primes you choose, this probability is going to be lower and lower and lower. So this is what it says in theory. Well, I normally tend to break it down to understand this easier. So let's say we don't accept this. Let's see what we can do. Suppose we are an adversary and we want to see what we can do. So let's see what was the description of the discrete logarithm problem. So given the generator G, some integer Y, and prime P, we know that Y equals to, there was a X that we raise it to the power G mod P, and then we get Y. So we need to find X such that this equation holds. That is our goal. So given G, Y, and P, we need to find some X so that G to the X mod P becomes Y. So that is our goal. Suppose that, okay, I know that, the adversary can start to, use the computational power to pre-compute these groups, right? So what I can do is that I can go ahead and create tables and pre-compute for many different tables. So this is the adversary algorithm. What it would do is that I'm going to choose G mod G to the 1 mod P1. Okay, so let's say this is my X and this is my Y. So, and then G to the 2 mod P2, and then G to the 3 mod P3, P1, I'm sorry. Actually, let me just give you the easier example. Okay, I'm sorry. Let's just make it easier. The example that I want to give is very big. So suppose that adversary knows this G and P that, this crypto system is going to use, or maybe Alice and Bob, they share and they're working on this group Z star P, and well, they would share this information publicly, so adversary would know that. So the adversary is here. What he's going to do is he's going to generate a pre-compute some of these values. So this is going to be x, this is going to be y. He chooses x to be 1, so he computes g to the 1 mod p, and then he chooses x to be 2, so g to the 2 mod p, and so on and so forth. So he chooses x to be 3, so it says g to the 3 mod p, and so on and so forth, right? Until some point, he can pre-compute these entire things. If or p is large enough, he would have, in the best chance, some of these entries, maybe I don't know, some integer a, he would have g to the a mod p, all the way to those computation. So whenever he sees this problem, what our adversary would do is that he would query this table for y. If given this y, he would go and search over here to see if he has the corresponding y. And and if he gets any heat, then he would return the x, the column responding to this same row. So he would return x, right? So you may wonder that how much chance our adversary have. I'm just restricting that example on the theorem above. So if your prime that you're choosing is a small, then then it would really make sense for adversary A to go ahead and pre-compute this table. He doesn't care about looking up this table. He can do hashing and he can pretty much do it very fast. Let's say those are not a concern, and this table can be very huge. So that is what we know. But at the same time, Alice and Bob know that this adversary can go ahead and pre-compute this table so that they publicly publish P. So the only chance that we can make sure that no matter how much computational power this adversary put over here, Alice and Bob are going to choose a very large prime number, a big prime. So for example, of let's say 1,000 bits, right? So if they choose such a thing, then in order for adversary to pre-compute all the elements, he has to go through a for loop of order 2 to the power 1,000, right? That is the number that we can generate with 1,000 bits, the maximum number. So we know that this is a huge number, and good luck with this adversary for going ahead and pre-computing, all these values. We know that this for loop would take years, centuries, and this is not going to be feasible. So even though we know that this is the case, and the adversary cannot solve that, we never say that he can never solve any of these problems. He might be able to solve some of them. He can go ahead and pre-compute, let's say 10,000, 100,000, or whatever that is feasible for him. So we say that the probability for this adversary to win this is very negligible. It's negligible because no matter how much he put to pre-compute them, these values, he's going to pre-compute, let's say, if this is the entire set that we are going to cover, maybe the adversary can pre-compute only this portion, right? So even maybe much smaller than that. I'm being very generous now. So you will see that at the end of the day, the probability that you really choose some value that it lands over here is going to be very small in practice. And then that is why normally we tend to choose a very large prime number, and that is the reason where you see that we never say, in formally discussing, we never said that there is no chance for the adversary to pre-compute it to solve this problem, because we know that for very, 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 very few instances, there is a chance that he has pre-computed these values and then he can return, just do a table lookup. But other than this pattern, as long as we choose our prime in a that we call it a safe prime, then generally there is no better algorithm for adversary to solve this problem rather than just doing this lookup or pre-computation. Okay, so that's how from now on we are going to make sure that for cryptographic purposes, whenever we are going to generate a Z star P, or P has to have some specific properties, which is stated over here, and it is the best to have this, this specific format. All right. Any questions?
Yes. When we said this, not all primes are like this. Not all primes are 2 times themselves plus 1 would make a prime, right?
Yes.
That's something we would have to test.
Correct.
Okay.
So what the next question you can ask me is that how many primes do we have like that they have this format and things like that. So very soon we would get to that and we would have a very good discussion about them. Any other questions? All right. If no question, let's take a break for 10 minutes and then we will come back.